Hey guys, this is Anthony. Today we're going to be diving into linear algebra. This is quite a long video, so feel free to watch it in 2 times speed and skip over the content you already know. I'm going to be putting timestamps at the bottom of the video so that you guys can do that. Our focus is basically the linear algebra that you need in order to do quantum computations, specifically quantum computing. So I guess to start, what is linear algebra? And linear algebra, I guess, kind of hard to explain, but it's essentially, talking all about vectors. So a vector normally looks like this. So if we call a vector v, and it has a little flag on it, and a vector can represent a lot of different things. More generally, it's in a vector space, which we're going to talk about a little bit later. It's a space that satisfies certain properties. But for now, we'll just talk about like the most common vector space, which is just like the xy plane. Or pretty much any spatial thing you can think of is generally a vector space. So normally vectors we write as like AB. If this was a 2-dimensional vector, this top part refers to the x-coordinate, and this bottom part refers to the y-coordinate. So if we have the vector, say, 1, 0, that would go right here. We generally draw a vector as an arrow going from wherever the arrow originated to the end there. So this would be probably something like 1, 2. So if you're writing it as a point, it would be 1, 2. In the vector notation, it's kind of this like column of 1, 2. So that's a vector. And vectors can be any kind of dimension. So we could also have a vector with many entries. Here's x sub 1, x sub 2, and it could actually go all the way down to some arbitrary number of entries in the vector. So this would be an n-dimensional vector. That's not really super important right now, but we will get to that, I guess. In quantum notation, we would refer to a vector, instead of using this like column format, AB, we actually, sorry, not the column format necessarily, but we have like, instead of this V with a flag, this would be right in here, and we have a psi. So this thing is called a ket. And it's basically the notation we use when we refer to a vector in quantum anything. So I'm not going to use this right now, but it's pretty important. We also have things called matrices. So these can be lots of different things. It can be kind of vectors stored all in the same place, or oftentimes it's actually an operation we can do on a vector. So matrices are, an m by m matrix would look something like this. So we have like A11, A12, A13, blah, 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 all the way to A1n. And here we have A21, A31, blah, 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 all the way to AN1. And then on the diagonals, these are going to be the same. And I think you guys can kind of get the pattern that this will eventually go to, this is an n by m matrix. So on this side, it's actually going to m instead. That's my bad. I was doing an n by n matrix instead. So the first one refers to the number of rows. Second one refers to the number of columns, which I spelled wrong. Okay. So now we're going to talk about, how do these objects, I guess, interact with each other? So let A be B matrix. Then we can have matrix addition, matrix multiplication, just like we do with normal numbers. The properties are a little bit different. So if we have A plus B, so let's let these be like two-dimensional matrices. So A would have A, B, C, D. And instead of using the subscripts like I did here, because those can be kind of confusing, I'm instead just calling like A1, 2, I'm just calling that B. So that's kind of the correlation there. And then I'm going to have B be X, Y, Z, W. So the operation A plus B, we would just add the top left with the top left of the other one. We would add the top right, respectively. So basically, each of these elements get added to each other. So A plus B would just be A plus X in the top left corner, B plus Y in the top right, C plus Z, and D plus W. This is our new matrix, which is defined by addition. In addition, just like in numerical addition, matrix addition is, forget the name actually, it might be transitive or reflexive or something, but it's kind of where you can switch them, and they're going to be the same thing. I wish I knew the property name, but maybe I'll add a note later. So this was matrix addition. Now let's talk about matrix multiplication. So now we have A times B, which is we're going to write as AB, and we're going to use the same values we have here. So I'm just going to write these two kind of next to each other. So we have ABCD times X, Y, Z, W. And what we're going to do here is multiply, and I would always remember this, row by column. So I'm going to leave a little note on the side. Row by column. Okay, always remember that. I have a lot of physics friends, and sometimes they forget this. So basically, we look at this row on the top here, A and B, and then we look at this column here. What we're going to do is we're going to match this element to this element, and then this element to this element. And add, we're going to multiply the two with matching colors, and then we're going to multiply these two and then add the result together. So this would become AB plus XZ, or sorry, my bad, AX plus BZ in the top left there. So notice this was the first column and the first row. So it goes in the first column and first row of our resulting matrix. If we then get rid of all these colors that I drew, I accidentally got rid of a little too much there. Now we look at this row and this, this row and this column. Remember this, we're still at the first row, but now at the second column, which means we're going to go to this spot in our resulting matrix. So this is going to be AY plus BW. And then if we keep going, follow the pattern, CX plus DZ and CY plus DW. This is now our matrix multiplication. And something that's important is that this property in addition is not true of addition. So A times B does not equal B times A. Very important. Okay. So now I know that. So we can also have the matrix transpose. This is just a little thing where if we have matrix A is a matrix, then AT, so if we have A11, A12, A13, A21, A22, A23, A31, A32, A33. If we have this matrix, the transpose of that matrix, which is this A with a superscript of T, this is the transpose, we would simply swap. We would kind of, if we treated this as a line, we swap everything across the matrix. We kind of reflect it. All right, so this is still A11, but now we just swap these indices. So this position used to be A12, now it's A21. And this is A31. A12, A13, A22. And I think you guys kind of get it. I don't want to have this video take too long. If we have a column vector or column matrix, which this can be thought of as a vector, so let's call this A, whatever. And then the transpose of that would just be now the row version of this. So this is now 3, 1. And this can be kind of important when we define the scalar product in the future. Another important matrix is the identity matrix. So just like we have the identity in multiplication and addition, in normal math, which you probably haven't heard it called that, but the identity is 1 in normal math. We can have the identity matrix, which is the same thing, but in matrix operations. So basically, we're going to call it I. We want it to satisfy the property that I times A is just going to be A. Just how, like, if we have a number x, 1 times x is equal to x. And we also, because matrix multiplication is when you swap the order, it's not the same thing. We also want it so that AI is also A. Okay? And I'm not going to go through the proof or anything, but this matrix does exist, and it's the matrix where there's all ones down the diagonal. So this is the identity matrix, and we should keep that in mind. There are also things called inverse matrices. And these satisfy the property that if we have A times A to the negative 1, so this is called, if you have a negative 1 in the superscript there, that's an inverse matrix. And if we have A times A to the negative 1, this will be the identity matrix. And same thing if we swapped the order. Okay, and there's some theorem where this exists and is unique. I'm not going to talk about how to compute it because it's slightly complicated. It's not too hard, but it would just take too much time for now. Just know that if you see that symbol, it means the inverse matrix. Okay, we talked a lot about matrices. We're going to go back to vectors for a little bit. So, something I want to talk about is called the norm of a vector. It's generally written as kind of 2 absolute value signs. I'm writing this really poorly. But this is basically, it kind of refers to the length of a vector. Although, depending on what kind of object you're using as a vector, it can differ. But for our examples, this is kind of, in Euclidean geometry, it's similar to Pythagorean theorem. So if we have, x1, x2 is our 2-dimensional vector, then the, and we're going to call this x, then the norm of x is going to be the square root of x1 squared plus x2 squared. And if we have a n-dimensional vector, v1, v2, all the way down to vn, then the norm is still square root, but it's just going to be each of these terms individually squared. So yeah, that's kind of the length of a vector, and I think it's kind of clear to see, if we treat this vector, oopsies, that's my eraser. If we treat this vector as a triangle, this one has slide length 2, this one has 1, then it's pretty clear that this, which is the hypotenuse, has a length, square root of 2 squared plus 1, which is square root of 5. So that's a norm. Now we're going to talk about the products of vectors. So there's 3 different types of vector products. That is the inner product, tensor product, or outer product, and cross product. So we're going to start with the inner product. So this is also called the dot product, which you've probably heard of in some of your physics classes. And this is basically, if we define, if v1 and v2 are vectors, if we have this dot in between them, this is a type of multiplication. It's basically if we have v1 is, I'm actually going to call these x and y. If we have x is x1, x2, and then y is y1, y2. So basically what we do is we look across here and we take the first 2 elements, we add those together. Then we do the same for the second 2 elements, add those together. And then if it kept going, we would do the same thing down there. So this dot product is going to be x1, y1 plus x2, y2. All right, so that's our dot product. The dot product geometrically, if we have, this is v1 and this is v2, they can have an angle between them. I'm going to call it theta. And there's a thing where if we take the dot product of these 2 vectors, then it's the norm of each of them. And sometimes the norm you can write with just 1 line. I'm just kind of doing this for clarity. But you might also see like just v like that, just like the absolute value. Because, this kind of looks weird. And then it's these 2 times cosine of theta. So the dot product, what it kind of measures is how, first of all, like how big they are. That's what's coming from these magnitudes here. But also, it has a component of their direction. So if these 2 were exactly the same direction, then that's when their dot product is maximal. If they are in 2 completely different directions, aka they have a 90-degree angle, then their dot product is actually, it's minimal, it's actually going to be 0. And that's because if we plugged in 90 degrees here for cosine, that's actually 0. So when 2 vectors are 90 degrees apart, we call them orthogonal. And the reason we say orthogonal instead of perpendicular is because, once again, vector spaces can be much more than just a 2D plane or a 3D plane. Sorry, 3D space. It can mean a lot of different things. So this is kind of our new term for perpendicular in linear algebra. And it's actually defined as when the dot product is 0. So v1 and v2 being orthogonal means that their dot product is 0, or inner product. There's also the vector product. So as you can see, the inner product, we multiplied 2 vectors and we got out a scalar. here we're going to multiply two vectors. Or sorry, it's not a dot anymore. Now it's a cross. So I know I have x there and y there, but this here is like the multiplication type of x. And I'm going to introduce something called a determinant. So determinants are properties of matrices. And they have some neat uses, I guess. Let's just call these what they are. So I'm going to start with a 2D matrix. Actually, we're going to do this one later. So there's an operation called the determinant. It can be kind of related to area in a way. But if this is our matrix, then the determinant of this matrix, so let's call this matrix A. This is going to be AD and then minus BC. And then now this one, so what we kind of did there is we went like this way, and then we subtracted going that way. Now what we're going to do is we're going to take this component, ignore these columns, and then take the determinant of this one. So this is A times the determinant of this submatrix. And then we're going to do the same thing. Now we take B, and then now our submatrix is kind of weird. It's like if we started it here and ended it here, and that's going to cause a minus sign because we're doing that. And then we're going to do the same thing where we select this and we do that. So this, I would just kind of remember this formula. I mean, that's a little bit of the process behind it. I can't really explain it super in depth. This is going to be A times EI minus FH plus, actually, sorry, that'll be a minus, B times DI minus FG, and then another plus C times DH minus EG. Okay. We're going to have V cross U. And V is going to have our normal components that we use. So this is like, when I'm saying V sub x and U sub x, that means like the component of that pointing in the x direction. So if I'm to draw a 3D plane, then if the vector is going this way and then up, then this is its VZ here. Its VX would be this way, and then its VY would be right there. So the cross product is actually defined as the determinant of a matrix. So this would be the determinant of a matrix that we define as x hat and y hat and z hat in the top. So if you don't know your hat vectors, they're called these are called unit vectors. And it's basically, if we're going to this drawing, x hat would be 1 in the x direction. And, you know, if this is x, this is y, and this is z. I'm actually doing that different than normal, but that's fine. This would be y hat, this is x hat, and this is z hat. So it's just 1 in that direction, basically. The determinant would be, we then write the components of V, the components of U, and this determinant is the cross product. So this is actually going to give us a new vector. All right, so it's going to be VYUZ minus VZUY x hat minus VXUZ minus VZUX y hat plus VXUY minus VYUX z hat. And just to clarify once again, x hat would be the vector 1, 0, 0. Y hat would be 0, 1, 0. And z hat would be 0, 0, 1. So when we add these all together and multiply them by their x hat, y hat, and z hat, the vector we come out with, it would result in a vector, and basically this part would go here, this part would go here, and this part would go here. If that makes any sense. So it's called the vector product because it gives us another vector. This inner product is also called the dot product, and it's also called the scalar product because it gives us a scalar. Forgot to mention that earlier. Okay. So a property about this vector product is if we have two vectors here, these are both in the xy plane, then the cross product will always be perpendicular. So this is v cross u. The cross product also has this formula kind of similar to this one in the dot product, which is that it's their norms, which I'm just writing 1 now, times the sine of the angle between them. So if this is the angle between them, now it's times the sine. So if v and u are orthogonal, that's actually when the cross product is maximal. And when they are parallel, their cross product is 0. So I'm going to write that parallel, 0, orthogonal is maximal. Okay, one more product to go over regarding vectors, and that is the tensor product. So if we go back to dot products for a bit, that's why we kind of start with them. This kind of this property can also be expressed using matrices. So if we treat x, so this is x dot y, right? If we treat x as a row matrix instead of a column matrix, so in this dot product we treat it as a column matrix, but this is actually just the same thing as x transpose as a vector times y, and not even using a dot product. It's really just like matrices. So this is the same as doing this. And now if we just apply matrix multiplication, we go row by column, this is going to give us the same value of x1, y1 plus x2, y2. If we kind of take this format here, I'm going to copy this, and we say, well, what happens if we just switch it? Okay, so now let's put, well, not necessarily put this one over here, but now switch it so that x is now the vertical matrix and y is the horizontal matrix. What happens? Well, we go row by column, right? So we start here, look there. And this is actually going to give us another matrix. So here it's going to be x1, y1, x1, y2, x2, y1, and x2, y2. So if you don't know what a tensor is, that's fine. I'm not sure I even know the details about it, but you can kind of think of a tensor as a matrix. Technically isn't, but it's fine for now. So in our scalar product, we got a scalar. In our vector product, we got a vector. And now in our tensor product, we are getting a tensor when we multiply these two. This is important in quantum. You really don't do much with it in actual linear algebra. Okay. We've talked a lot about vectors and matrices. Next thing is talk about what a vector space is. All right. It's kind of a whole new section. So now I've kind of mentioned it so far, basically, it has all these properties it needs to satisfy. They're not super important, but if I go to my linear algebra notes, actually, I was just looking at this. These right here are the properties it needs to satisfy. So, you don't really have to. You don't really have to care about all these. Here, I just highlighted it. This one is just saying that if you add two vectors, it's also a vector. This one is just saying that if you multiply a vector by a scalar, then that's also a vector. Kind of those are the most two important. But let's go back to what we were talking about. I don't know if I ever mentioned scalar multiplication, did I? So, in a matrix slash vector scalar multiplication, if I put a scalar A in front of a matrix or a vector, this is just the same as multiplying each of those elements by that scalar. And that property needs to hold to be a vector space. Another important thing is that a vector space must include the origin. So like the vector 0, 0 has to be in the vector space. A subspace is a subset of the vector space. So essentially if this whole plane is a vector space, right, then I can choose a subset of that vector space. So say I just chose, this half of the space, right? This is a subset of the vector space. I'm not sure if it's a vector space yet. I would need to try and prove it, and it turns out if I prove it, it would be wrong. A good example of a subset of the vector space is a line through it, and it would have to include this point in the origin. I'm not going to delve super important into that, but these are called subspaces, and there's a few subspaces that are important to know. Most important one is span. So if I have the span of, two vectors, x and y, this is basically all the vectors that I can add x and y, or some multiple of x and y, and I can get that vector. So, and b and r can be any real number. So they can be fractions, decimals, irrational numbers, etc. So like say I have this is x and this is y. If I add these together, I can only get something along the x-axis, if I drew my axis better. So that kind of shows how span is in that regard. If I have y here pointing a different direction now if I add vectors in a certain way, I can access like this area and this area of the plane. And this is really important once we talk about bases. So like for example, if I wanted to get this vector right here, I could probably add x one time, add x another time, subtract y, maybe. Or maybe I was adding y in those cases there. I'm realizing now I didn't talk about adding vectors geometrically, so we'll do that for a bit. Basically, if I have x plus y, and x looks like this, and y looks like this, I just basically pin y on the end of vector x, and I get this new vector. Here, this is x plus y, okay? If that makes any sense. Just briefly touch on that. All right, so now I want to talk about something called linear independence. Linear independence basically just means that one vector can't be just the sum of another vector. So if v is linearly independent to x, then I can't, no matter what I try to do to x, I can't get v by just doing a scalar multiple of x. So like, for example, y is linearly independent to x because no matter how many times I add or subtract x, I'm not going to get to y. I'm just going to stay on that plane. So like, if v was, so this means that v is not a scalar multiple of x. And if I added more vectors here, so it's linearly independent to 3 vectors, it can't be any combination of those 3 vectors. And what's important is that a basis of a vector space is a set of linearly independent vectors where the span of those vectors equals the vector space, if this is our vector space B. So as you remember, as I talked about earlier, the span means that if I add x and y in certain multiples of each other, then it'll cover all of this space, right? So that means that x and y actually are a basis of the vector space. So if I wanted to have any vector in this, I could get it with x and y. Now, if I wanted a vector that has a little component in the 3D direction, so like say it comes up here, but it actually is coming up a little bit, which I can't draw, I actually wouldn't be able to get that vector with just x and y. I would need one more vector, okay? So, and basis kind of refers to how many dimensions there are too. The number of vectors is the dimension. Okay, there are some bases that are a little better than others as well. These are called orthonormal bases. And this is plural, the E. This is plural. This is singular, by the way. So you remember this ortho term from orthogonality? This basically means the vectors that make up the base are orthogonal to each other. So the whole reason when we draw axes, they're all perpendicular to each other. And the reason we do it this way is this is the best way to like represent the entire plane in the most like simple manner. So like x is perpendicular to y, and y is also perpendicular to z. So x hat, y hat, and z hat actually are an orthonormal basis. Sorry, I didn't talk about the normal part yet. So ortho means 90 degrees apart. The normal part means that the norm of the vectors is 1. So it's much simpler to deal with when you multiply something, it doesn't actually change. If I multiplied x hat with something, it wouldn't actually change the magnitude of the thing I applied it to. And that's just because it's normed so that its magnitude is 1, which you can see here. If I did square root 1 squared plus 0 squared plus 0 squared, that's just 1. And that just makes it easier to work with. So x hat, y hat, and z hat are a basis for 3D space, which you might sometimes see as r cubed. All right. Some other bases that you sometimes see is like cylindrical coordinates or spherical coordinates if you've looked at Calc 3. Yeah. So now I want to talk about something called linear transformations. So if we multiply a matrix by a vector, so this is our matrix A and this is our vector V. Something happens to it, right? So we have AV1 plus BV2, and we have CV1 plus DV2. And this is another vector, right? So actually what we did is we took some vector V1. I'll draw a new axis. Took some vector V1 and we actually we moved it around some way. We actually put it maybe over here or something. And this is called a linear transformation. So a matrix acting on a vector can kind of explain some sort of motion. So say we only wanted the x component of a vector. That would just be the matrix 1, 0 on the matrix, because if we have 1, 0 times x1, or I guess xy, if these represent the x and y coordinates respectively, this is now just the x coordinate. So you can call this a sub x, and this matrix will only give you the x coordinate. Another example I like to use is if we define the matrix R equals cosine of theta, negative sine of theta, cosine of theta. This acted on a vector will rotate counterclockwise by theta in 2D. So that's just kind of interesting. I'm not going to go through that, but it just shows you how rotation, a lot of the stuff we're going to be doing with quantum circuits and just quantum states is actually these matrices acting on vectors, and they do a transformation. So you might hear the term linear functional being thrown around by probably Carson, who's doing the intro to quantum stuff. Or maybe Rishi or someone. I'm not totally sure. Okay. That is our linear transformations. And there's a lot to be explored there, but I've already probably yapped enough. All right, there's a couple last things I want to talk about of good importance. I know that this is quite a long video, but I'll try and make it short, and that is the eigenvalue problem. So this has applications in rotation, quantum physics, obviously, differential equations. It's basically if we have a matrix A, then if we treat that matrix as a linear transformation, we multiply it by a vector, then when does that result in the vector just becoming a scalar multiple of itself? So this lambda is a scalar, and a scalar just means not a vector. It's just a number. So, n or whatever. And visually this means, if we have our 2D vector space here, and this is our x, then after the operation A is applied to it, it's going to reside somewhere along this line. So that is basically what this is doing, which means that it's not shifting around at all. and that's important for calculation reasons. So what we can do is we can subtract the lambda x from both sides, and this becomes a lambda I. This is the identity matrix, if you guys remember. So identity matrix, where, if you guys recall, I is 1, 0, 0, 1, and then if it was more than 2 dimensions, the ones would just keep going down like that. Okay. So we have this times x is equal to the 0 vector. I haven't talked about the 0 vector yet, but it's basically just a column of zeros. What a surprise. So it's basically every entry in that in that matrix is 0. And that'd be true for any matrix, not just like the 0 vector. Okay. And there's a theorem basically that for this to have non-trivial solutions, and by non-trivial we just mean x isn't just the 0 vector, because obviously if x is 0, 0, then no matter what we apply to it, a matrix times 0, 0 is just going to be 0, 0 again. So that's always going to be true with the eigenvalue problem. So we're interested in the vectors where that is, where x is not just the 0 vector. So non-trivial solutions happen. There's a theorem, I don't know the proof of it, but where the determinant of that matrix, A minus lambda I, when that equals 0, we have non-trivial solutions. And this is called the characteristic equation. And we solve for its roots, just like how you would solve for roots in a pre-calc class or a calculus class. To find the values of lambda. So these are called the eigenvalues, and they correspond to eigenvectors. So if we, if there's a times x1 equals lambda 1 x1, and there can be other vectors where the matrix also, where this property is also true, but it would have a different value of lambda. Okay, so the lambdas are the eigenvalues. The vectors are called eigenvectors. Okay, that's just some terminology in that regard. And lambdas can be complex as well. So lambdas can have a real component and an imaginary component. And I'm going to talk about imaginary numbers very soon here. So by soon, I mean, I guess right now. I want to kind of wrap up this video with kind of, what are the things in quantum that are different than just classical linear algebra? So the first thing is something called Bra-Ket notation. It's kind of clever because, bra and ket are just like bracket, So basically, you'll see this symbol psi a lot, and it has this horizontal line to the left and then a thing on the right as well. And we call this a ket, basically. And this just represents a vector, okay? And kind of almost in the same way we've been thinking about it. The only difference is now it's a superposition, which I'm sure Carson will talk about soon here. And what's nice about this is if you see something like this is a bra. And this doesn't always... This can usually mean like an operator or a linear functional. It's not necessarily a vector unless it looks like this one. But instead of doing like, A dot B to define the dot product or the inner product, now we define the inner product as something that looks like this. And similarly, the outer product would look something like this. So those are some kind of important notations. I didn't talk about this earlier, but when I talked about tensor product, this is also called the outer product. So kind of it's the opposite of the inner product. The inner product, which is also the scalar product, took us from two vectors to a scalar. This one takes us from two vectors to a tensor or a matrix. So kind of some parallels there. You know, if this is an operator, then we can have it act on a state, and this is kind of the same. It's analogous to the linear transformation. My handwriting sucks. Okay. And I also want to talk about complex numbers. So if we have a complex number z, this has a real component a and an imaginary component b. So if we are in the real and imaginary plane, then this vector kind of resides here, and the a is the real part and the b is the imaginary part. And because of Euler's identity, which looks like this, e to the I theta equals cosine theta plus I sine theta. I'm not going to go into why that's true or how it changes the eigenvalue, but basically saying that z equals a plus bi is the same thing as saying z equals c times e to the I theta. Okay. Where now this hypotenuse is c, it's the magnitude of the imaginary number, and this is the angle or the phase. And it's pretty clear here that, you know, if we take cosine of theta, if we take this e to the I part, it'll become this whole thing. And the cosine of theta just corresponds to a down here, and then the sine of theta corresponds to b. That's some classic trig there. So you can kind of see the parallels geometrically there. There's also something called the complex conjugate, which is just if we subtract the imaginary part. So our complex conjugate lives down here. This is z conjugate. I think also it sometimes looks like this. Not totally sure about that. Okay, going back to our quantum state, which is normally using the Greek letter psi. That's what this symbol is here. It's psi. Okay. The vector space of quantum states has a basis. Okay, so we talked about bases before. So the basis of it's called the Hilbert space. That's not really important though. It's two vectors. It's the 0 vector, which is just 1, 0, and the 1 vector, which is 0, 1. So these are kind of familiar, using the columns to represent vectors. And basically any quantum state is a sum of these. So alpha times 0 plus beta times 1, where alpha and beta are complex numbers. So in that way, even though there's only two basis vectors, there's kind of 4 degrees of freedom, because each of these complex numbers has a real and imaginary component. That is pretty much everything I wanted to talk about. I know this was kind of long, but I think we got a lot done. And if you guys have any questions or want me to go through any examples, I would have loved to go through an example of the eigenvalue problem, but I think with time-wise it would have taken way too long. So thanks very much, and I'll see you guys at the meeting.